All right, let's move on now to prediction, which is much more clear. It's very easy to predict for new data. With these nonparametric methods and tidy models, we just use the predict function, right? Easy. So you put the model in, you say predict, and here you pass in the new data that you want to predict for. So for example, here, if this new, let's say x1 and x2 are biomarkers, and y represents onset of a particular disease, if a new person walks in the next 5 years, if a new person walks in and has these x1 and x2 values of their biomarkers, I just construct a little table and I put it in the predict function, and this is going to give me the risk of them getting the disease in the next 5 years, at least what the model thinks that is. So as always, the hard part isn't getting the predictions. The hard part is measuring how good your predictions are. And we've been down this road before, and we're gonna do it again. You can see it's very similar. For nonparametric regression, it doesn't change anything. You want to know, compare the actual outcome to the predicted outcome and say how good it is. So we've seen this before as well, that regression methods can memorize the data, but actually be very far from the truth. So here I fit a regression tree, a very, very deep regression tree, I think like depth 20 or 100 or something like that. And you can see that it's actually hitting all of the training data points. Now, this is the true conditional mean that I know because this is a simulation. And this function is actually not that good of a fit. However, the training error is 0. So that's why we need to use test error. We need to use a different sample of the data that was not used to fit the model to compute the mean squared error. And that's going to be a good estimate of the generalization error, or quote unquote population error, which is the error that we would get if we took this model and applied it to the entire population and compared the predictions on the entire population to the outcomes on the entire population, not just in the sample that we got. So how do we get at that is it's very simple. We split the data into training and test sets. We've seen this. We train on the training data. So here script A represents our machine learning algorithm, like a random forest or linear regression. Doesn't matter. So that gives us our guess of the function. Then we predict for the values in the test data, and we generate our predictions, and then we compare those predictions to the true values, and that's going to give us our test set error. So in tidy models, I actually already showed you how to do this. It's quite simple. So we have to split the data at first. You can put different amounts of data into the training or the test sets, depending on whether you want more data in the training set will give you a better model, but more data in the test set will give you a better estimate of the performance of that model. So there's a bit of a trade-off there. So you split the data, and then once you have this kind of split data object, you can call training or testing on that, and that will give you the data frame with just the data in this testing split, or just the data in the training split. And you want to fit your model on the training data, and then you want to predict for the testing data. And here I'm gluing on the testing data again so that we can compare the truth to the predicted value. So actually, we already did this. I'm not going to do it again. You can try to do it without going back to the earlier part of the lecture. You can always go back and see that if you want to compare. Now, we've already talked a little bit about hyperparameters, and let's get back to this. This is really the only kind of trickier part of doing machine learning relative to linear regression or methods that don't have a lot of hyperparameters, which is that you need to figure out how to set these things. And we already saw these in the context of splines, right? We have here this LM, and we're doing the spline, and we want to say, what is the degrees of freedom that we should set? So if we set this to be low, the fit that we're going to get is pretty smooth. And if we set this, by smooth, I mean it's not too wiggly. And if we set this to be higher number, like 11 or 90, we're going to get very, very wiggly fits. And it seems like some intermediate value is giving us the best prediction in terms of being closest to the true value of the function, which is this dotted line here. So how do we set these things? And what do we mean by hyperparameters? So in any method, any machine learning method, the parameters are values that the algorithm is going to find. So for example, for linear regression, before we fit the data, we don't know what the coefficients are going to be. After we run LM tells us what the coefficients are. So LM is in charge of fitting the coefficients. Now, what is LM not doing? LM is not figuring out what the value of df is. You're giving it df. So hyperparameters are anything that the user is providing, and the parameters are anything that the machine learning algorithm is fitting. So for a decision tree, for example, you don't have to tell it what's a parameter is the values of the split, where it's splitting, and what the predicted values in each of the leaves are. Those are parameters. The decision tree is going to figure that out. What you have to tell it is how deep do you want the tree to be, right? Or these other ones that we didn't really talk about too much. That's okay. Random forest, it's going to fit all the trees and do everything for you, but you have to tell it how many trees you want. It's not going to figure that out for you. So all of these methods have different hyperparameters that are user set values that you kind of need to know a little bit about in order to make reasonable choices. Or do you? So we're going to see that actually we can automate a lot of this, and you don't really need to know that much, which is great. So let's look at this again. We already saw this a bit last lecture, but we noticed that there's this kind of sweet spot in model complexity that minimizes the population error. So if we look at the training error, it's always going to be going down because we can get arbitrarily good fits of the data by adding more and more complexity to our model, and we're going to nail all of it. But that means that actually the fit, if you look at from here to here, the fit has actually gotten worse in the population because we're not observing the population data, but that's represented by this kind of gray line. That's the function that we would like to be fitting. So the population error may be decreasing, but then it's going to start increasing at some point because this is what we call overfitting. We are overfitting the training data, which means that we start to fit worse on the population. So there is some kind of sweet spot. How do we find it? So here, for example, it was 21. df equals 21. Well, we can use test error, right? So if we make a plot of test error, you will see that the test error is generally following the population error, and we can pick the spot that has the lowest test error. Now, the only downside to this is that it does require us to allocate precious data to the test set. So we know if we put more data in the test set, we can get a better estimate of the population error, but that means that our model is fit with less data, which means the model is not as good. So what we can do instead is this cross-validation. We didn't talk about this last time, but we could have easily. I just decided to talk about it here instead of last time. But the idea is this. So let's look at just this kind of looks complicated, but ignore all this stuff for now, and let's just look at this. So we take our data and we split it into 4/5 training data and 1/5 test data. We train the model with the training data, and then we evaluate it on the test data. That will give us this. So this is a single number, like RMSE. RMSE is equal to 10. Okay. Now, we forget about all of that. We go back to the original data. We split it again. So this time, instead of this being the test set, we're going to pick this as the test set. And the rest of the data is going to be training. So we're going to train the model again. And this is now going to be a different model because it's trained using different training data. So we're, so like let's say it took 2 minutes to train the model. We're going to take 2 minutes to train a totally different model. It's the same model. It's the same hyperparameters. But it's going to, like let's say you did linear regression here. You're going to get some coefficients. If you change the training data, you're going to get different coefficients. So you get a different fit. And this is going to give you another root mean squared error for this test set. So let's say here it's going to be 10.5. And then you repeat. You go here, maybe you'll get 11. You go here, you get 9.4. And here, maybe you get 10 again. Okay, so you're just changing which part of the data is being used for testing and which part of the data is being used for training. And then here, you're going to average these all together. And, eyeballing that, let's say that's about 10. Okay, and that's going to be your final estimate of error. Now, the reason this is nice is because you have not split off any amount of data that is only being used for testing. You're always using some of the data for training and some of the data for testing. And this is the average, even though each of these test sets is small. So you can kind of think of this as like averaging, let's say that each test set only has 10 observations. Well, that's not going to be very good because the sample average of 10 observations is pretty noisy. But if you then average that 5 times, that's going to be less noisy. So by averaging over multiple small test errors, you're going to average out the variability test error, and you're going to get better estimate of the test error, less variability. You're not changing the bias; it's still unbiased. You're just reducing the variance kind of for free of that test error. Of course, the thing is that here you actually have 5 different models, right? This is, again, with linear regression, you might imagine this is one set of coefficients that you get when you use this training data. Here you have a different set of coefficients. Here a different set of coefficients. So which model do you use? Well, none of them. You're actually going to retrain using all of the data as the training set. And that model you will never evaluate because you have no test data left. You used all the data for it. But you can use this number as an estimate of the performance of this model, because this is the average performance of these 5 models, and this model is going to be very similar, if not better, to all of these 5 models because it has more training data in it. It's actually going to perform better. And moreover, yeah, it's going to be different than these, but these are 5 different models. The average of these is going to be representative of the average model that you're going to get when you train using this algorithm. So that's the idea of cross-validation. And it's used more often than a kind of hard test train split, actually, especially in cases where you have smaller data sets. If you have 1 billion observations, who cares? Just split off 1 billion to do it. Just split off 50 million to do testing, 50 million to do training, because training with 50 million observations, you're probably not going to do any better than training with 100 million. So you don't even need that extra data to improve the accuracy. So you can kind of afford to lose as much as you want for your test set. Moreover, you don't even your test set, the variability of the test set error is going to be so small anyways because you have so much data. It really doesn't matter, basically. You can just do a hard split, call it a day. But if you have 100, 200, maybe even 1,000 observations, cross-validation is generally the way to go. Thankfully, it's very easy to do cross-validation in tidy models. Instead here of initial split, you're going to say v_fold underscore CV. And here v equals 5 means that you're going to do this 5 times. So you're going to split the data into 5 chunks and then shift the test set across those 5. You could say 10. You could say 20. And actually higher is typically better, but since you have to redo the model fitting process as many times as you have folds, then you're paying computational price for doing this. So higher is better statistically, but you have to pay more for it computationally. But that's kind of a nice, it's actually fine because in practice, if you really want to get a more accurate estimate when you have very small data, you care a lot. So with very small data, maybe you want to do 30-fold cross-validation. But since the data are so small, it's so fast to fit the models, it doesn't matter that you're doing 30-fold. Whereas in really, really huge data sets where you really can't afford to refit 1 million times, it also doesn't matter because your test set is so big that who cares? So this is not really a problem choosing this, basically. You can just choose this for computational convenience. Make this as high as you can as long as you're willing to wait. So that's how you set it up. And this will give you some data structure here that's very similar to the thing that you get from initial split, where you can call training and testing on that to get the training portion and the testing portion. The only difference is that for split data, you're going to have this kind of structure here where you have 5 different, let's say for v equals 5, you're going to have 5 different folds. And those folds are in this object called, so if you do split data, $splits, $1 or bracket 1, you're going to get an object that has the training and the test data. So I've gotten, if I index just the first one, I basically have this, and then I have test and train. If I index the third one, I have this, and then I have train being these parts and test being that part. So this is the syntax to get that. So this is if I just want one so-called fold of the cross-validation structure. But of course, what I want to do is loop over that. So within one fold, I'm just going to train my model on the training data and predict on the testing data and get the RMSE. So that's doing within one fold, getting this RMSE number. But of course, I want to repeat that for all the folds. So I can just put this into a map where I'm mapping over the data. I should have actually called this maybe like fold to be more clear. Let's just change it. That's nice. Okay. So the training data for this fold, I'm fitting my model, then I'm predicting for the test using the testing data in that fold. And I'm getting the testing RMSE within that fold. And that will give me, well, let's just do it. I just want to show you. So let's just rename, let's call this data. Y charges and x equals age, just so you can see. Oops, data. Okay. And then let's do that 5-fold cross-validation. So I'm setting up the cross-validation, saying split it up into 5 folds. It takes care of that for you. You don't need to worry. And then I'm going to do random forest in each fold, compute the RMSE, blah, blah, blah. So this is what I get. So this is the, yeah, so y on x, yeah. So this is the root mean squared error in each fold. So this is in the first fold, the second fold, the third fold, so on. So these numbers are exactly these numbers here, fold 1, fold 2, fold 3 performance. And then if we want the overall error, we can just average that. So here we can do, for example, mean. There we go. So that's the root mean squared error, the cross-validated root mean squared error, which is like test error. It's an average of test errors. So this is also a good estimate of the generalization error. Okay, so the reason I'm showing you that is because you can do the same thing here, like to pick these hyperparameters that you want to, for example, depth. How deep should I make the tree, or what DF should I put in my splines, or what learning rate should I use for the neural network, or how many hidden units? Like all these things, you may not even know what these things mean, but you can pick what they are by trying a whole bunch of different stuff and trying a whole bunch of different combinations, and then picking whatever combination gives you the lowest test error, or picking whatever combination, if you want to not do test error, but you have maybe a small data set and you want to do cross-validation instead, pick whichever combination gives you the lowest cross-validation error. And this strategy of kind of throwing a whole bunch of machine learning methods, because you could even try a decision tree and a linear regression and a neural network, or a neural network with 100 hidden layers and a neural network with 50 hidden layers. So you have like 5, 10, 100 different models that you're trying, all of which have different values of the hyperparameters, and just throw it all at the wall and see what has lower cross-validation error and go with that. And all of that is completely fine, as long as you then have a final test set that you're using to evaluate the error. And in the model selection part, you're evaluating based on the cross-validation error. So that's also fair. This whole strategy where you're using cross-validation to pick among a whole bunch of different hyperparameters or machine learning algorithms. Sometimes people will call that a cross-validated ensemble, or a more Berkeley-specific term is superlearner. There's also the superlearner package, which is kind of like tidy models. And so this is a term that you might see in the literature as well. It means basically the same thing. So in tidy models, let's do it. So here, I'm going to set up a bunch of different models. I have a decision tree, and that decision tree here, when I do the tree depth, and instead of saying here's the depth that I want, I'm going to say tune. So this is a special function that comes from another one of the tidy models packages. I think it's called dials. And here I'm just going to say tune because I'm saying I don't really know what that is yet. Here's what I want to try. So I have this other thing called grid. And grid, I say I want to try tree depth 2, 4, and 10. I don't know which one is going to be best. I want to try all those. So that's my decision trees. Then I'm going to use this other method, KNN. What's KNN? Doesn't matter. Let's say I look at KNN and I look at the help and I see that there's these hyperparameters called neighbors and weight function, weight func. I don't know what they do. I don't care. I'm just going to say tune and tune. And then I'm going to make this grid and I'm going to say try neighbors 3, 6, 9. Now it helps to know a little bit about these methods because I kind of know that these are going to be reasonable values and I shouldn't try 10,000 and that -3 doesn't make any sense. And weight func, I'm going to try rectangular, triangular. So this is going to create a grid of all the possible combinations of these values for the KNN model. And then linear regression, there's no hyperparameters. So I just say grid equals NA. Now in my tidy models structure, now what I'm going to do is do the cross-validation. I'm going to set up the cross-validation. And what I have to do is I'm going to map over these models. And for each of them, I have to do this. Like the details of this are not super important for you to understand. You can always ask ChatGPT to help you kind of put this together or copy paste this and then try to break it up. It's more like just coding and admin than any kind of understanding. Conceptually, what we're doing is just selecting between all of these possible combinations using cross-validation. So I'm going to make this workflow with this model. I'm going to say I want to predict y given all the predictors, and then I'm going to run this tune grid. And tune grid is going to basically look at this grid of all these different hyperparameters and evaluate the cross-validation root mean squared error for every combination of these. And then since I'm looping over my models, it's also going to do it for all the models. So when I then run this collect metrics function, which is also from tidy models, again, the details not super important, just kind of admin. I mainly more want you to understand the concept. This is what I get back. So let's scroll. What I get back is this. So it's a list with these three different objects: decision tree, KNN, and linear regression. And you see for decision tree, we have this table with tree depth. Tree depth equals 2, 4, and 10. Now mean here, this corresponds to the root mean squared error. Standard error, this is the variability of this across the testing folds. So one of the nice things about cross-validation is that you get these 5 different, for example, 5, 10, however many, 5 different estimates of test set error. And since you have 5 of them, when you average them, you can also look at the standard error of that average. And so you can get some amount of a measure of the variability of the test set error as well, instead of just a single number. So that's what we're seeing here. So these are the test set errors using this depth, each of these depths. So we can see actually that there's not a big difference. Basically, like depth 2 is pretty good. You get a little bit better with depth 4, but depth 5 or higher than that doesn't really improve things. Now for the KNN, it actually stands for K nearest neighbors. You have every combination of number of neighbors and the weight function. So here, while I was using rectangular weight function, whatever that is, who cares? For 3, 6, and 9 neighbors, you can see that kind of 6 was the sweet spot here. And then it went up when I hit 9. And similarly, but for triangular, it seems to be going down actually as I keep increasing the number of neighbors. And this is the lowest we've got. And then for linear regression, this is the error. This is the standard error. This is also interesting. You see that the linear regression is more stable because the standard error is smaller. So across different subsamples, across different folds of the data, the linear regression model was kind of giving me the same kinds of predictions every time. So it's more consistent. It's more consistently bad. Whereas the tree-based models, you can see this is that variability that I was talking about. They're in different training data give me test errors that are kind of different because the model is more different. That's why this is higher than this is here. So anyways, the final conclusion is that this is the best. If you look at all these cross-validation errors, well, in fact, these are all kind of good. But I would say, let's just go with this, right? This is the one I would choose because it's the lowest error. Since these are tied, I mean, they're probably not. There's probably some decimal points here, and I would guess this is slightly lower. So this is what you can go with, is the smallest one. All of this was like almost totally agnostic to knowing anything about what any of these methods do, how they work, what these tuning parameters mean. You can throw it all at the wall, use cross-validation to pick the best thing. So this is how I would select a model. I would almost never go at a problem and a priori say, you know what, I think here a decision tree is going to work, or I think here linear regression is going to work, or I think here I have to use... No. Anytime I see a prediction problem, I'm going to approach it and just say, here's my 10 algorithms with a whole bunch of reasonable hyperparameters. I'm just going to mash this against the data and see what comes out. As long as you're selecting based on cross-validation error and then doing a final test set to estimate the test error or an outer loop of testing, this is good. There's no problem with this, okay? So let's have a look at this. So we want to predict charges, regression tree. We don't know what depth to use. So let's do this. So here we can basically copy paste what we've done. This can be a little simpler, I think. Let's do this. So let's do 5-fold cross-validation on the insurance data. And we have charges, regressed on everything. And this needs to be charges. So here we have our, let's do our decision tree. So let's just set depth equals to 5 for now, so you can see what we're going to do. And again, I'll set this thing to 0 so that doesn't mess with it. Okay. Oh yeah, it's called tree depth. There we go. Okay. So there we go. So these are the cross-validated errors on the different folds. We know we should be averaging them. Just do mean. There we go. So for depth equals, so this is for depth equals 5. We can change this to depth equals 10, rerun it. So we get a different number. Okay, so we want to basically vary that between 2 and 30. So we can just put all this in a loop. So this whole thing, so let me call this folds. Okay, and now here, this whole thing, we're gonna map over tree depth. So we have 2 to 30. That's what we wanted. So this is our tree depths. And so I'll say this is a function of depth. Depth. Okay, so let's see what happens. What did I do? Oh, I didn't run that first code. There we go. So this is the test error, or this cross-validation error for depth 29, depth 20, so on and so forth, right? I can make this a little bit tidier as well. I can do, here I can, where did it go? Here I can output, let's call this CV error. And then here I can just output typical CV error and depth. And now I can call this map underscore df. Okay, so there we go, CV error and depth. So let's save that to CV errors. And now we can make a plot. Sure. Okay, there we go. So it looks very similar to what we generally expect with these kinds of things. So here, depth is regulating the complexity of the model. So it's like adding more degrees of freedom to the spline. Obviously, we can fit the training data better. We're looking at something like this, right? If we add more depth to the tree, the first a single split will just be like one step, right? Or two different steps because we have 2 leaves. And then if we go a layer deeper than that, each of those 2 buckets will themselves get split. So we have these like 4 steps that we can fit. So it's getting more complex as we increase the depth, which means that we can get better and better fits of the training data, but that doesn't necessarily mean that we're going to get a better fit of the population data. And after a certain point, we're going to be overfitting. So this is exactly what we expect to see. We have training error, or the error is decreasing because we're decreasing the bias, but then after a while, the variance is taking over and we're getting a population error that's higher. So this is our cross-validation error, and this indicates that the best error, you could look at the actual, you could find the minimum here. So let's do that. CV errors. Let's filter for CV error is the minimum. So it tells us the best depth to use is 4. So if I were to want to generate a model to use in practice, I would then go back and do this again. But you would just use all of the data. Here you use the best depth, which is 4. There we go. So this is the model that I would take to use in practice. Now, if you're clever, you realize I haven't actually evaluated this model because, well, there's a funny thing that happens because I've done model selection here, right? So the fact that this model was the lowest, this is fair to select between these different models, but this is actually not an accurate estimate of the capacity of this model. So typically, what we could do is have an outer layer of if you want to go the full complexity of what we would actually do in practice. Let me just make sure this is all gone so that we can have it be clean. We would do this. So at very beginning, I would split. Let's say we could do an initial split. Okay, so do this. And then here, when I do the cross-validation, I'll only do that within the training of that split. This all happens. That looks the same. Now here, I'm going to train using the entire training data. So the cross-validation has happened inside of the training split. And now I fit using the entire training data. And I can predict on the testing data. Oh, it's called splits, sorry. Okay, so this is the final kind of test set estimate, which you can see is actually a bit higher than this. So this is all biased a bit down, or this is biased a bit downwards because it's what I used to select the model. So there's kind of like a multiple testing problem here. It's fine for comparing, but I shouldn't use this as my final estimate. I need another test set. A little bit of complexity there. If you're I don't want to get too much into that. But if you're curious, you can look up training validation test split. So you have the validation section that you're using for model selection, and then a final test set that you use for predicting. So this is what I would, if I were publishing a paper, I would say this is my estimate of the test error of this final decision tree that I chose using cross-validation based on the internal cross-validation within the training set. That's more than you'll need for this course. We're not going to talk about that.